Hello, welcome to the fourth and final video of oscillations. And as you can see on the screen, this is actually a very classic setup of the Barton's pendulum, and I think we actually have this setup in our physics lab. So if you happen to see it at the back, you could play with it, ask for permissions first. So you will notice that I'm going to share the desktop audio because the music is perfect, okay? And I got this off a physics teacher from Singapore. So link down below if you want to give him more views. But I'm just going to play the first half. So here you will notice that there's a periodic driver. And this periodic driver is going to swing at a certain frequency or period determined by the length of this string. So the longer the string is, the longer the period. We have established this already. And you will notice that on the other side, you will have different cups at different length of string. So when the periodic driver start oscillating, right, energy will transfer from the periodic driver to all these cups, and they will be forced to oscillate. Now what I want you to do is actually pay attention. Pay attention to the music, but also pay attention to the amplitude of the oscillations as well. All right, so you will notice that it's gonna get stuck in your head for the whole day. Okay, so you will notice that the one with the same length will have the largest amplitude, and this phenomena is what we call resonance, where the force frequency, because you notice that they are all forced to oscillate. Okay, to save you a bit, I shall mute it. Okay, so you will notice that they are all oscillating, but there's this one special cookie that's oscillating with the highest amplitude possible. This is actually how phone works. Let's say you have your mobile phone with you, and also Bluetooth lah. So later at the end of A2 we'll talk about communication, but let's say you give my phone a call. Do you know my number? Did I give you my number? I give you my number all the time, everywhere, in every notes. Okay, he's back again. So you will notice that when we change the length, the frequency will change. And you can see, although everything is forced to oscillate at the same time, only the one with the same length will oscillate with the highest amplitude. So to talk about this phenomena of resonance, right, I kind of want to explain a bit to you how communication works. Let's say you were to call someone. This will send up a radio wave. Don't forget, all of this has to do with wave. So the radio wave will have a certain frequency that is unique to your phone number. How does your telephone know your phone number? SIM card lor. You know there's a SIM card inside there. So when I call, let's say I call your phone, my phone, which is the periodic driver, will send out a radio wave at a certain frequency, and then send through the tower, send through all the cell tower, and by the time it's near your area, your phone will respond because it is pinging the exact same frequency like this. Now, last time in olden days, right, it's harder for us to fine tune. So sometimes you will get cross-tapping, or you hear some other random person's phone call. I don't know whether you are too young to know this. But yeah, so right now, this resonance will allow one circuit to talk to another circuit without actually having a connection, a physical connection. All right, so before we go into all that deep stuff, we're just going to talk about what exactly is a driver frequency, what exactly is a forced oscillation, because as usual, today is A-levels, and we got to learn how to write out definitions properly. All right, so let's go. So here, you can see this page 4 and the last page of your notes. There is actually a variable frequency oscillator. So this one is your force frequency. And there's a metal cube here with a spring that will be allowed to oscillate at any at its own if you pull it down. So I'm going to talk about a few key definitions. The first one will be the free oscillation. So free oscillation happens when I turn off the oscillator. Meaning, if let's say I were to go back to the styrofoam cup situation just now, I don't oscillate the periodic driver, I just oscillate all the cups. Okay, so free oscillation is when you turn off the vibrator and you pull down the metal cube a bit and then you release. So the metal cube will oscillate at its own little frequency. Okay, so we define oscillation as a free oscillation as an oscillation where the only external force, so there's no extra forces, no one is forcing it to oscillate beyond the initial disturbance, nothing else is oscillating it. So the only external force acting on it is the restoring force, or in this case it will be the tension in the spring. Okay, there is no damping. Damping here is known as loss in energy. So if you lose energy, that's called damping. Alright, so there's no loss in energy, it's allowed to freely oscillate forever and ever. Okay, so if you have a free oscillation, the oscillation's frequency is called the natural frequency, which is the frequency of a vibrating body undergoing free oscillation. So of course this would depend, in this case of a spring mass system, would be dependent on the mass and the spring constant. Okay, so again, they can ask you to define this if they feel like it. Okay, so we're going to talk about the force frequency now, meaning now I turn on the vibrator and then I force the metal cube to vibrate at my frequency. So a suitable analogy here, right, would be to adjust that frequency until the vibrator frequency is the same as the natural frequency. It's a little bit like this lah. Your natural frequency might be wake up at 12 p.m. noon and sleep at 3 a.m. Maybe that's your natural frequency, but MCKL makes you wake up at 7 to come to college at 8. So you are like very low energy because you are forced to oscillate at a frequency that you don't like. Okay, but there will be some amplitude lah. Alright, so here I will change the vibrator frequency until it is the same as natural frequency. So this force frequency, right, the actual definition is actually to turn on this one and then change the frequency so that the spring will oscillate together with the particular vibrator. Okay, and since this one has its own, the metal cube has its own natural frequency, so I'm just going to label the external as FEXT and the natural frequency as Fn. Okay, so periodic frequency here is defined as a periodic external force. So in this case, it will be the college timetable, making you wake up at 7 a.m. or making the object vibrate at the applied or the forced frequency. You might not like it, but still gotta go, man. Still gotta go it that way. Okay, but if just so happen the force oscillation is also the natural oscillation, then you get magic or resonance. Okay, and this occurs when the applied frequency or the force frequency or the driving frequency, they are all the same thing, which is the frequency of the vibrator, is equal to the natural frequency. So if college changes the timetable and then you can have class at 12 noon, maybe you are more energetic lor, maybe you're happier lor, okay? Maybe you will resonate. I'm not sure if you're resonating with my lame jokes, but yeah. Okay, anyway, equal to the natural frequency of oscillation, external equal to Fn, and what will we observe? Think of the pendulum just now. The amplitude of oscillation is maximum, the biggest possible. Alright? So to map out this relationship between amplitude and applied frequency, we will sketch out a curve, which I call a resonance curve, okay? And I will draw different resonance curve depending on the degree of damping. Now, what is degree of damping? Degree of damping is actually how much energy is lost in the system. If the degree of damping is very big, means that a lot of energy is being lost. If degree of damping is 0, means no energy is being lost. The oscillation can go on forever and ever and ever and ever, and it is not possible because friction. Okay, so let's say now I'm going to plot the amplitude of the oscillation. versus the frequency. Even if the frequency is not natural frequency, even if it's not resonance, there will still be oscillation, just that the amplitude is small, S-M-A-O-L, small. All right, so force frequency or driving frequency, and I'm going to change the driving frequency, okay? I wish to highlight that, although I didn't label here in the video, that this is not zero. I didn't start the driving frequency at 0. If the driving frequency is 0, and then you get my graph, it's going to be very weird. So it's okay if the graph doesn't touch the x or y axis, and you will see shortly why. So this dotted line is actually the natural frequency, Fn, right? And we are now going to draw a series of resonance curve for different degree of damping. Yeah, the graph, they can ask you to sketch the graph. So this one, where Fn is actually an asymptote, is no damping. In other words, it's not possible. Mathematically, we know that the graph looks like this, but in real life, we don't know. If you want to know the maths, come ask me in person, because this one is uni level mathematics. But if you're doing further maths, this is in your FP2 paper. Alright, anyway, let's go back. So if I increase the damping, then you will get this kind of peak graph. First thing you will notice, right, is that the entire peak is being shifted slightly towards the left. Okay, and the next thing you will notice, okay, now I don't like the shape, so I'm drawing it again, is that this thing is not symmetrical. Okay, it's not symmetrical. You should never draw it symmetrical, because you know, when the frequency is small, of course the amplitude will be small, less energy bah. Alright, so frequency is higher, then you will get a larger amplitude. But that aside, you will note that this one, it seems like I'm touching the x0 amplitude axis. Very weird lah. So this one is not 0, okay? I cut scale for both. I did not start from 0 frequency. If 0 frequency then got amplitude, it means that you never oscillate, but then it oscillates itself. I know it's dark outside, but I'm not scared of ghosts, but are you? So I don't think it will oscillate on itself, okay? So now I'm just being picky about the shape. That's why you can see repeated drawing, just for my own entertainment. So again, there's a slight shift, and you will notice that the peak is less and less sharp. So when they ask you to sketch this, which is pretty common in past years, the more damping you have, the frequency will begin to shift and decrease slightly at an increasing damping. The natural frequency will shift. Why? This one you wait until uni lah. We need a lot of calculus to answer this question. Okay, so you just need to know the trend first. The natural frequency will drop, and the peak will also be less sharp. So we're increasing the degree of damping. Alright, so your natural frequency, FO, decreases. So you can see that there is a shift towards the left, slight shift. And at the same time, the graph is less sharp. Okay, and the amplitude will of course decrease as well. Please never draw symmetrical. This graph is not symmetrical. Okay, so you might be thinking, Miss, if you increase the damping, got name or not? Is it a little bit of damping? No lah, we call it light damping, lightly damp. Okay, and then the next level, critical damping. And then the next level will be heavy damping. Okay, all this actually got mathematical definition one, but this part not really needed lah. Okay, I will teach you how to identify them from the graph, not from the equation. Okay, so light, critical, and heavy damping. So we will define damp oscillation now. You see, damp means very wet. And the reason why we want to think about damping the oscillation, I will explain later. But we define damp oscillation as resistive forces causing the oscillation to lose energy over time. And sometimes we do want the oscillation to lose energy. You know why or not? Okay, so I'm going to draw out the graph. By the way, this is types of damping. Every year I forget to change this mistake. My bad. types of damping. Okay, so the reason why we want damping is because certain systems should not resonate. It should not have a lot of energy. Okay, and the reason being, we don't want the thing to oscillate. So an example for that would be the car suspension system, or the spring that is inside your car tire, so that when your car passes through a hump, it doesn't oscillate like this. Okay, so for lightly damping, this which is what I'm drawing now, you can see I'm trying to sketch out a nice sinusoidal curve with a gradually decreasing amplitude. Okay, this is what we call light damping. You can still determine the oscillation. There is still a fixed period. However, the amplitude is decreasing bit by bit. So this is what we call light damping law. All right. So the characteristic of light damping will include, right, exponentially decreasing amplitude, and also having the same period or the same angular frequency omega. All right. So this is the simple displacement against time graph. All right, so the decrease is slightly exponential. I can show you the equation, or you can find the equation on Wikipedia, but totally not needed lah. All right. So this is what we call lightly damp or light damping. And from here, you can see that the amplitude decreases gradually. Normally we call it exponentially lah. Okay, but the frequency and period remains the same. Okay, next. We are now going to look at the next variation of damping, and that would be your critical damping. Okay, so for critical damping, right, you will notice that it will return to equilibrium position very quickly, as soon as possible, without actually really oscillating. Okay, so this would be critical damping. The oscillating system returns to equilibrium position as soon as possible. Okay lah, a bit silent as I draw graph. Shall play you some music. Alright, the next version of damping would be heavy damping. So for heavy damping, right, you will notice the difference between critical and heavy is that heavy almost treats the equilibrium position like an asymptote. So it takes a long time for heavy damping or over damping, same idea, to return to equilibrium position. Alright. So you might be thinking, Miss, got example of all these damping. Okay, so while I transfer the graph back into the notes, I will tell you what the examples are. Critical damping is like your car suspension. You want it to return back to equilibrium position as soon as possible. Okay, over damping, because think about it, if your car suspension system is light damping, means you pass through a hump and then your car go like that for a long time. Motion sickness. Okay, if your car has over damping, it's even funnier. Goes through a bump and then it stays at a slightly higher position for a long time, meaning as you go through more and more bumps, your car will get higher and higher. So weird. Okay, so example for critical damping would be a suspension system. It would be like, you know, when you open the door and there's a spring on top of the door to slow the door from closing. That one would also be critical damping lah. It could also be over damping. Actually, I think the one that is on the door can be classified as over damping. You don't want it to close as soon as possible. Sounds very violent. So for cars, we want critical damping. For doors, we generally want over damping. Another example of over damping would be your mattress. I mean, if your mattress, spring mattress, is like the blue graph, the light damping graph, or then it's like sleeping on a water bed lah. You turn a bit, the bed will bounce up and down. Your dog jump on your bed bounce up and down. Very tired like that, cannot sleep leh. Okay, so for mattresses, good spring mattresses, we would prefer to have heavy damping so that it takes a long time to ease back up into the original shape. Okay, critical damping generally is pretty sudden. We use it for car suspension. Okay, so hope that helps. And we're going to look at the next thing now. So here I will demonstrate or use Walter Lewin's demonstration. By the way, he's a pretty cool physics teacher, to show you resonance in breaking a wine glass. So you have the driver system, which is the speaker here, and the force oscillating system, which is the glass. So if you have any glass, right, and by the way, if you see me in person, I'll bring a wine glass to class and then we can play with this, not break my wine glass. But you will notice that every wine glass has a certain pitch, okay? So if the frequency of the sound wave is the same as the pitch of this glass, and the varying pressure wave, because sound is also a pressure wave, the varying pressure causes the glass to oscillate. So I show you lah. Okay, so let's see how that looks like. And so I'm going to modulate the sound a bit, because the pitch can be quite high, especially if you're wearing headphones right now. Calm down a bit. So he's going to turn on the strobe lah, or turn off the light, so you can actually see the edges of the glass more clearly. I think you can hear that sound. Now observe the rim of the glass. You will notice that the glass rim is oscillating, and as he changes the frequency, the amplitude is actually increasing more and more. Wow, you can see it oscillates so much. So this is where resonance happens. You can hear a very loud ring, and also large amplitude. Is it going to break? Is it going to break? Is it going to break now? Okay, you wait for a bit lah. It takes a while. You need that violent vibration to break down the structure, the molecular structure of the glass. Especially where there's imperfection, you can see there's already a crack here. So you need to hit the note and hold it there until it breaks. There we go. In slow motion. Alright, so we can use the human voice as the driver frequency to break down sound wave as well. For that, you can check out the Physics Girl video in the description on your own, and I will see you in the example video. Bye bye. Don't go randomly singing to wine glasses at home lah. Huh? Later your mom call me. I ain't gonna replace the wine glasses that you break at home. Bye. See you in the example video.